right, didn't get any requests for questions this morning. Sorry, I make myself shake this morning. Still kind of bleeding. Didn't get any requests for questions this morning, so I've got the chat up if you need it. Again, these are not lectures, these are not lessons, these are office hours. So if you have questions, post them to the chat and I'll answer them. There's about a minute lag here. So when you post, it's going to take me about a minute to see it and hopefully respond. And that's assuming I'm not like responding to something else. So again, I'm here if you have questions, but otherwise, these are just office hours. So just got a question, what is meant by a bulky group? And does it refer to atomic weight? And more or less, yes. I'm going to say more or less yes. That's not technically what it refers to, but it correlates really well with it. So a bulky group is whether or not that carbon adjacent to the ring is primary, secondary, tertiary, or quaternary. So the more things that carbon has attached to it, the bulkier it's going to be. But things like bromine and iodine, these are huge groups and they don't have anything attached to them, so those would be considered bulky as well. So yes, you can use kind of like atomic weight as a first pass approximation. The reason why I don't necessarily say like it's that the best way to look at it is that if we look at something like propyl, so let's say we have a propyl group and we have an isopropyl group. So your isopropyl group here is going to look bulkier. These things weigh the same thing. It's a CH. They do weigh the same thing. We're just kind of rearranging where the carbons are on it. But this keeps a lot of that bulk of the weight closer to the ring, whereas this group kind of trails off. So it kind of, even though it's big, it does kind of stick off and does have the ability to like flop away. The isopropyl group's a lot more sterically hindered. But again, these are kind of esoteric cases. Yes, atomic weight's a very good way to look at it. And then if you're looking at carbon groups, primary is smaller than secondary, which is smaller than tertiary. So yeah, so when we say primary, so primary is smaller than secondary, which is smaller than it's primary, secondary. Secondary, tertiary, and quaternary, because we're going to include the bond to the ring. So primary, secondary, tertiary, quaternary, these are getting increasingly bulkier, even if they, for whatever reason, happen to have the same atomic weight. So yeah, concentration of atomic weight is a good way to look at it. So how concentrated is that atomic weight around? Because this kind of scale with atomic radius. Now, a bromine versus a methyl group, that's kind of up for debate. So bromine's kind of limited by its atomic radius, whereas that methyl group's got 3 hydrogens hanging off of it, so you can make a case for either. That'd be interesting. Let's do a Google search. So I only see one response. I am kind of curious. Oh, there's actually a quantification for us, the A value. A values are numerical values used in the determination of the most stable orientation of atoms in a molecule, as well as the general representation of steric bulk. A values are derived from energy measurements of different cyclohexane conformations of monosubstituted cyclohexane chemicals. So, the A value of bromine is 0.38, whereas the A value of a methyl group is 1.7. So people have actually gone through and tried to calculate this. This would be an interesting thing to add to the notes. So the A value, and I'll just write it up for people to see, are people's attempts to quantify this. And it actually almost looks legitimate. I mean, I haven't really had time to really read it. But to do this, we would go to a table of A values. Wow, this is cool. We learn something every day. And the bigger the A value, the more it wants to be in the equatorial position. So it's got, So methyl group is 1.7. An ethyl group is 1.75. So in this case, an ethyl group would actually push out a methyl group, but they're probably roughly the same. If you have, come on, where are you? Tert butyl group, that's an A value of 4. A isopropyl group is 2.15. So to answer your question, apparently people have already built tables of these to address this issue. So again, this would be something interesting to add to the notes next semester. I mean, it's kind of esoteric. I really wouldn't recommend, like, you would never be giving something that ambiguous on the exam. You're welcome. Oh, awesome. There's actually exceptions to this. So carboxylic acids are an exception. They actually prefer the axial position. They don't like the equatorial position despite them being the bulkier groups. And it has to do with electronic factors. Now this isn't cyclohexane, this is a cyclic, it's a 6-membered ring, but it's got an oxygen in it. But yeah, usually if it doesn't obey these like general rules, there's usually like more going on with the electronics. Cool. Learn something every day. So the next question was when you're drawing 2D projections of the practice pack, doesn't matter how we number the stereo drawing the 2D applications. No. As long as your structure is consistent with the stereo drawing. So how to practice drawing these. I think you're just about dead. So let's say we had this 2D drawing and you wanted to draw it as a let's see, you're talking about taking the 2D drawings and projecting it back. So there is some rules with how these are drawn. you need to make a choice as to, so I don't want to give you the wrong impression about this answer. So this is why we're going through these examples saying, can you figure out if they're axial or equatorial relative to one another? So there are some books that are very diehard that this is carbon number 1 or this is carbon number 1, and it depends on how you view this projection. So some books view this as these are the arms of the chair, this is the top of the chair, this is the bottom of the chair. When I was taught it, these are the arms of the chair, this is the top of the chair, this is the bottom of the chair, and so that's where those 2 1 positions come from, is that it's a matter whether you think that tip's the top or you think that's the top of the chair. But the thing is, it doesn't matter. You can rotate it and you can get multiple answers. So the only rule is that one of these has to be axial and the other one has to be equatorial. So if you draw this, and the first one you come to, so if you're looking at the ring, so we're moving in a clockwise direction around the ring, the first one has to be axial, the other one has to be equatorial, and they have to be on the same side of the ring. So as long as your stereo drawing is consistent with that, so as long as you pick these so that works, your answer is still correct. What you're going to find, and we'll work through it really quick, is that it's every 2 carbons. So this projection is correct. So is this one. And if we move along, so is this one. The reason why this would not be correct is that, let's see. So the first one's equatorial, the second one will be axial. This may actually work too. So if we take this drawing and convert it back. So let's make this the number 1, let's make this the number 2. So that axial's down, when we fold it down, it'll be down. That one's up, it'll be down. They're the same. We should probably stick a methyl group in there just so we get rid of that rotational symmetry. Okay, so if we take that one, flip it over, okay. So, you can't pick any 2 and draw them. The reason you can't pick any 2 and draw them is that, so particularly if we have an ethyl group and a methyl group. Let me build that ring. So here's the ethyl group with the methyl group. So if we define this as this top carbon here, pop it up, pop that one down, we're going to have it going up and over, and we're going to have this one going off to the side. So that drawing would be correct. And if we take this drawing, there is a rule about how to draw this particular ring. And the rule is that these 3 corners all have to be up. So the axial here has to be up, the axial here has to be up, and the axial here has to be up. These 3 axials have to be down. So if you take this molecule and you only rotate it by 1 carbon, what you end up doing is actually having a flipped version of this diagram. So it will actually look like this. So if you only turn it what would be 60 degrees, you end up having to flip this drawing to accommodate it. But if you turn it 120 degrees, which basically brings you back to where you started, that still works. So if we make this the first carbon, this the first carbon, or this the first carbon, the points that are up all have their axial groups pointing up. So in this case, if we define this as an axial position, if it's up, then it has to be one of these 3 carbons. If we were to say, well, we'll make this the first carbon, so we'll ignore these 2, and we'll draw an ethyl group down, and we'll draw a group off to the side. Well, the problem is that in order to get that to work, let's say we interpret this 2D drawing as that this is the number one carbon. So this is the carbon that's up, this is the carbon that's down. We put our ethyl group going down, our methyl group equatorial, and then when we rotate it around, we can't get it, we get the mirror image. And the reason we're getting the mirror image is that this is defining the axial group is down. And so we're going to set the first carbon, if it's going to be axial, we're just going to set it up, and this is just for consistencies. But again, if you try to define the first carbon as anything other than these three carbons that are up, you'll end up getting the mirror image of whatever you're drawing, because this is really what you're working with if you're defining the first axial group as down. So again, I know it's kind of like really hard to see the stereochemistry of it, but it does matter which carbon you start as the number one. You have three choices, 1, 2, and 3, but you can't pick any of the 6 because there is a stereochemistry associated with it. With these 3, the axial groups are up, and so if you say, well, I'll set this as the number one carbon, now your axial carbons are pointing in the wrong direction for what would be considered the first carbon in this stereo drawing. Because by convention, what we do is we say that the first carbon is the first group. That's why we name it that way. But yeah, it has to do with the fact that that stereo drawing does actually have like there's real spatial implications with it. So it's like when you drew your Newman projections and like you had to be careful about where the atoms were relative to each other because you had to make sure it matched up with the model. This is kind of like an advanced version of the Newman projection. So it really, there is actually a physical 3D model it corresponds to. And if you're not careful about where you put your atoms, you'll end up getting like a mirror image by accident. This does have has what's called a C3 rotation axis, so you can rotate it. So right now you got a carbon pointed. We'll do all the axial groups pointed out at you. So I can rotate this 120 degrees and you'll never see the difference, but if I rotate it only 60, you'll notice that the axial groups actually point it back at me now. That's why you can't go with like the 2nd, 4th, and 6th positions in this drawing, because they're pointed the wrong way. Yeah, I know that's probably a really complicated explanation. I've never actually had anyone ask me it before. Yeah, you're welcome. number 6 on the naming discussion board. I've gotten the name, but I'm still stuck on the ordering them alphabetically. All right, courses. So this one, ooh, it's gonna be a big one to draw. Yeah, I was looking at your answer. You do have you've got the right components, and this is the nice thing about IUPAC. You've still got the right components, so you could easily draw it back from what you've got named, but it is not named correctly. Guessing that's a decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Because decane was the highest one I was willing to learn. So you've got the decane, and you've got 3 groups. You've got methyl, cyclohexyl, and cyclopentyl. So the way we look at these groups in IUPAC is that cyclo is just a modifier. It's still a hexyl group, it's still a pentyl group, it's just the cyclo is a modifier to say it's a pentyl group but it's in a ring, or it's a hexyl group but it's in a ring. And so we ignore the cyclo when we do the naming. We also ignore like the di, tri, tetra, and things like that because, again, those are just considered modifiers. They don't change the fact that it's a methyl, ethyl, bute, pro, pent, names like that. So we organize them in alphabetical order based purely on the number of carbons in the name, so that we don't, so if we did something like, let's say we had these 2 cyclo groups, well, if we did it by the cyclo, all the cyclo groups would be at the front and you would just have this running line of cyclo groups. That's really annoying because now you're basically saying all the cyclos go up front and then the next prefixes, like the linear chains, come next. And I think the goal here was to avoid creating priority for the ring groups over the branch groups because they are considered equivalent under IUPAC. So even though this is a ring and this is a methyl group, they're still alkane components. There's no reason to favor one over the other because they're equally reactive. So to prevent from implying that one group has priority the other, we ignore all the modifiers and just say they're all alkanes and we're going to list them in alphabetical order based on the number of carbons that are in them. So since H becomes before M, this ends up being cyclohexyl. Then we have methyl. And then we have cyclopentyl. And again, we're not worried. We ignore that cyclo because it is a modifier, and we don't. If we did it in alphabetical order based on the prefixes or the modifiers, all the cyclo groups would be at front, and that would somehow imply that they're important, and they're not. They're just as reactive as your alkyl branches. So now we've got 1 cyclohexyl, we've got a dimethyl, cyclopentyl, and since the cyclohexyl comes first, we're going to start from this end. And so we would get 5 cyclohexyl, 4, 7 dimethyl, 6 cyclopentyl decane. Now, this is also a good segue to point out that the IUPAC rule says whatever group comes first, but it doesn't specify, is it the group in the drawing or is it the group in the name that comes first when you assign priority. The way I was taught, the way I interpret the rule is to say that it's based on the name because that would be the easiest way to do it. But you can definitely see some textbooks that go the opposite and say it's based on the drawing. So what do we mean by based on the drawing versus based on the name? And again, I argue this is much more in the spirit of the rules. If we go by first in the name, I don't even have to look at the structure or do anything to the structure to know what group is setting the first carbon. I know it's whatever functional group comes first, and so I look for that first, and I look for the closest end of the ring. What you do if you go by the drawing is you go from the opposite ends of the rings and you start counting in. So 1, 2, 3, 4. Well, they're both methyl groups. So now I go to the next one, 5. So there's two ways to number this ring, and you'll still hit functional group. So if we number this 1, 2, 3, 4, 5, 6, 8, 9, 10. So with our old naming, we had 5 cyclohexyl, 4, 7 dimethyl, and 6 cyclopentyl. If we number it the other way, we get 6, 4, 7, and 5. And so books contend what's considered the first point of difference. So, okay, to kind of get around this, we also have the rule that we number them so we minimize the numbering at the first point of difference. So the first point of difference here is the 5 and the 6. So because this starts on a 5 and this starts on a 6, we would say that this is the better way to name it. There's also a set of people that say that it's the sum of the numbers. So if you add up all the numbers, you need to minimize the numbers. So we do, in this case, it doesn't matter because the orders are reversed. This is why that rule is wrong. And by the way, you'll never find a single textbook that says that. Yeah, we're learning a lot today. Yeah, you never put the cyclists first because you're implying they're more important if you do that. We'd never want to make that implication. This is actually a really good example. I didn't know that. So I just kind of made it for a discussion board. So the first point of difference here is going to refer to the position. So if we end up with a situation where we've named it both ways and we want to figure out which way is probably right, it's the difference at it's first point of difference. So these two numbers are different, whichever one gives us the lowest first number. This is going to be how we name it. So it ends up being 5476 versus 6475. Now again, you will find people that argue doggedly that you have to add it up. And if you add it up, you go with whatever one gives the lowest sum. Two reasons why I do not agree with that, and I have never found a single book that says that. One, that is a lot of work, especially with that first example where I gave you a tetramethyl, that 224455 or 224466. That is a lot of work to add those numbers up. That is not in the spirit of the IUPAC name, which is meant to be simple. The other reason why I know this is not true is because it can't tell you which of these is correct. So there are situations, there are very esoteric situations where you end up where basically all the numbers are the same except for like 2 numbers. And the question is, which one do you go with? The answer is always you keep reading left to right until you find the first difference, and you go with whatever direction gives you a low number, even if it raises the values for the others. You're welcome. So 2D projections versus stair drawings on the packet. So let me bring the packet up. So we'll go to the last problem, which is, man, it's so long since I've had to draw these. So we got this little monstrosity. Over, down, up, over. And we want to convert this from a 2D to a 3D projection. And again, I'm going to advocate here the easiest way to do this is with a kit. So we'll do it with the kit first, and then we'll talk about how I do it by looking at it. So we've got an equatorial group going to the right. So if we take our cyclohexane, we have to orient all three of these as being pointed up. So our model here is going to have the 3 atoms pointed up. The first one that's pointed up here, it's going to go to the right. The one counterclockwise is going down for the axial. This axial is pointed up. And this equatorial is pointed to the left. So again, I'm going to define these 3 carbons as having their axials pointed up. So I've got 1, 2, 3 axials pointed up. This axial that's got a pointed up has an equatorial coming off of it. This axial is pointed down in the back. This axial is pointed up. Oops. And this equatorial beside it is pointed off to the side. So I'm just going to take it, crush it down. And what I end up getting is this, and you wouldn't be able to name this without using RS, so we're not going to bother naming it. But we basically get 2 groups that point up and 2 groups that point back. And we can rotate this any way we want, but the point is that we're going to have 2 groups that are cis to each other that are beside each other. And another 2 groups that are cis to each other beside each other, but they're trans to the other 2 groups. So we're going to end up with these 2 cis groups, these 2 cis groups, but these groups are actually trans with respect to each other. So how do you do it without a modeling kit? And what I do is I draw on all the axial atoms. So I've got this axial up, this axial down. This one's occupied by a methyl group. This axial is down. This axial is up. So any axial groups above the ring. So anything that's on an axial position that's up is going to get a solid wedge for me. So let's arbitrarily define this is the first carbon. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So this axial group is pointed up, so it's going to be a solid. So this will be the 3rd carbon. And this axial group 6 is pointing down, so it's going to get a wedge. Now, what happens to the equatorial group of 1? Well, because its axial group is up, when we go to crush this down into a line bond drawing, it's going to push that methyl group down, so we're going to get a wedge. For this hydrogen, the axial is down, it would be a wedge, and it's going to push this one up. I'm sorry, this is a dash because it's pointing down. This is going to push it up into a wedge. And so I end up getting the same answer. This has just been rotated, what, 120 degrees? But we've got the 2 groups. These 2 groups are cis. These 2 groups are cis, but they're trans relative to each other. Now I do kind of see how this would be picking your poison because you're either going to struggle with trying to translate this into your model and then crushing your model down to get this, or you're going to struggle like defining where all the up down axial positions are. Um, yes, it's kind of one of those unfortunate things. I've just done it enough now. I kind of see it. This is why we just make you practice it a lot. That's why you have all these practice problems. Yeah, you're welcome. Wait, other questions out there? All right. No questions for now. I'll get a little bit of work done, but I am still here. All right, so last question before we sign off for today. Explain the pressure of a liquid in a container. So to think about this, and you're probably thinking about intermolecular forces and vapor pressure. So to think about this, let's start with a hypothetical container of liquid, and we're going to crudely draw out the atoms in the top of the liquid. And in this hypothetical model, we're going to assume that there's no gas phase vapor. So what happens? Well, there's two forces going on here. There is the force of translational energy, the want desire of these molecules not to be near each other. So there's a repulsive force, but then there's the attractive force called the intermolecular forces. So with intermolecular forces, these are the forces that hold liquids and solids together, and they range from very weak, which are the London dispersion forces, all the way to super strong, which are the ionic forces, with things between. So polar covalent, which is going to be your dipole-dipole, hydrogen bonding, and then there's metallic bonding, which we're not going to talk about. So at a given temperature, there is a probability distribution of energy. There is a distribution of energy of the different atoms within the liquid phase. So some are going to have enough energy to actually like pop out of the liquid phase and jump up into the gas phase. And when they do, we just get we start getting evaporation. So they start popping out. But at some point, but in the gas phase, they also kind of have their own energy distribution as well. It's going to be set by the temperatures. So some are moving fast and some are moving slow. Some are moving so slow, in fact, that they get actually reabsorbed by the liquid because they're not moving fast enough to get past these intermolecular forces. So what will happen is that some will begin to get back into the liquid phase and we start seeing condensation. And at some point, we'll reach an equilibrium. And at that equilibrium, the rate of the ones coming out, popping out of the gas phase, popping out of the liquid phase because they have enough energy to escape the liquid, because it's a distribution of low energy and high energy atoms, is going to match the rate at which the gas phase molecules are recaptured. So the rate of evaporation equals the rate of condensation. And this is where vapor pressure comes from. So vapor pressure is when we reach this equilibrium, when the liquid is losing molecules just as quickly as they grab it. So pressure in a liquid. So pressure in a liquid is, you've got two forces going on. So you've got kind of a bulk attractive force, which is your intermolecular force, and then you've got electron-electron repulsion. So what happens with electron-electron repulsion is that these molecules are kind of coated in electrons. And so as you start pushing them closer and closer together, these electrical forces are going to start pushing away from each other. And what we're going to get is really more like what's called a Lennard-Jones potential. So we've got energy and we've got distance between two molecules in a solvent. So when they're really far away, they don't interact at all. And as they get closer and closer together, they begin to see each other. And what's attracting them are differences in charges. So this molecule is going to have a slightly positive charge and slightly negative charge. And so as they get closer and closer together, they start to attract due to intermolecular forces. But once they start getting really close to each other, what will happen is that those intermolecular forces become we start getting a second force. And the second force is electron-electron repulsion. And so if they get too close, the electrons repel. And so we get this ideal bond distance here, D. Now, the intermolecular force here can also be in the IMF as well as, so what happens with liquids? So at room temperature, atmospheric pressure, they're basically kind of bouncing back and forth in this little well. They're pushing back and forth. Now, if you apply a force to a liquid, what you're doing is you're forcing them to get closer and closer together. And this pressure, this pushback you feel, is actually the electrons trying to repel one another. They're getting so close now that the electrons are actually forced to get close, and they're going to start trying to push off of each other because of those strong electron-electron repulsions. In electron-electron repulsions, individuals aren't that strong, but we're talking about thousands and billions and trillions of electrons all having to push off each other, so it's a death by 1,000 paper cuts. There are so many small electron-electron repulsions that end up being a large pressure pushing back. So the pressure you feel when you push against electrons or push against a liquid, that pressure is actually the electron-electron repulsion trying to push them away. So that's where pressure comes from in a liquid. If you have a sealed container and you try to compress it, the pressure that you're feeling pushing back is all the electrons trying to get away from each other. You're getting the molecules way too close together. And you can keep compressing and you can compressing, but the force you have to apply is going to match the energy it takes to get them that close together. So the best way to think about it is people sitting on a train. There is an ideal distance, but as you start pushing them into smaller and smaller places, eventually they start touching each other. And their physical bodies are actually going to start pushing back. And so this is kind of how that pressure works, is that the electrons are the physical body of the molecule. Get them close enough and they'll start getting close enough that they'll start having to push back against each other because they don't want to be compressed. All right, so that's it for the live stream today. Again, if you ever have questions, please feel free to email them in advance. And I will see you all Monday.